Okay, so let's get started. So I'm gonna continue the discussion that Peter started last time on Schriek descent. Well, let me recall the setup. So we're kind of, well, what are we trying to do? We have analytic rings. And then, well, we're going to build some geometric objects on them somewhat in the model of scheme theory, where you start with commutative rings. So the first thing you do is you define what are the affine things, and might as well just formally define them to be the opposite category of analytic rings. And then, so yeah, an object in here, maybe you call X, and it corresponds to let's say an analytic ring, which maybe one can denote OX, comma DX. So recall that an analytic ring consists of an animated condensed ring, and then a certain full subcategory of modules over that, of the, say, full derived category of modules over that. So I'll denote the first coordinate by O of X and the second coordinate by D of X in this notation. So here, I mean, X is really just a formal symbol here, but okay.
Yeah, and also in the derived context, you somehow use D bigger than or equal to 0 in homological notation,
yes.
which corresponds, in the case of simplicial ring, it's just considering simplicial modules.
Yes.
And taking the derived, at least
yeah.
the enhanced one is just this.
Yeah.
And I suppose there is a way to define the full derived category also.
Yes.
So, but I'm not sure how, but is it important to just restrict to the, can one do it?
For some purposes, it's easier when you, so the two formalisms are equivalent. You can either think of this, or you can think of the full thing.
Yeah.
And you can get back and forth between them. For some discussions, it's more convenient to consider the greater than or equal to 0 part to be the primary object. But for the discussion today, it's actually much better to consider this thing as the primary object. And the reason has to do with descent. So it turns out that the full derived category will have this Schriek descent, but the greater than or equal to 0 will not. So in other words, another way of saying it is for an analytic ring, we have a nice T structure on this category, but for a general analytic stack, there's not going to be a T structure.
So on which?
On the derived category of the global thing, so which is obtained by gluing these local derived categories.
So for an analytic, there is a T structure which is what?
For an analytic ring, there's a T structure, which is, so this thing is by definition a full subcategory of, derived category of OX modules.
Okay.
This has a natural T structure, and the claim is that.
You mean just the
yeah, you just forget down to derived condensed abelian groups. So the T structure is detected all the way down here, and the claim is it passes to, it induces a T structure here.
Okay, this is by Jackson. And by the way, what is your official definition of the derived category, like, let us say, for a simplicial ring? The full one.
Yeah, so when I talk about it, what I'm thinking of is the following. There is a functor from simplicial rings to, say, E1 rings, so meaning just algebra objects in this category. And then I just take modules over that algebra object in this category here. So I use some infinity category formalism of algebras and modules.
So like use IR algebras.
Yeah.
So it's not defined by, but it can be defined concrete. I suppose you can take like chain complexes of simplicial modules and take the totalization, take some quasi-isomorphism, model structure and 7C.
Yeah, no doubt, but I prefer to think of it like this. I mean, you can understand perfectly well, like, how to calculate with this definition. I mean, the free objects are like things in here, tensor with A, and then, you can make resolutions and,
So if you forget commutativities, then simplicial rings is the same as E1 rings?
Well, yeah, simplicial rings up to equivalence, of course, yeah. Yeah.
Okay. So let's go.
Okay. Okay, so right, and we singled out there was this definition. So a map is shriekable if it can be factored as an open immersion followed by a proper map. What was the definition of these concepts? Well, for a proper map, so let's call this F, and let's say J and then pi. So for a proper map, we have, this means that an element M in D of OX prime lies in D of X prime if and only if its image in D of OY, I mean image under the forgetful functor, lies in lies in dy. So in other words, you just take the class of complete modules you have on this analytic ring, and then inherit the notion of the notion of completeness up here. So just given the data of this ring, you can always do such a thing. You can define this d of x prime to be ones where you forget down and you ask it to be complete there, and that always defines an analytic ring structure, and those are exactly the ones corresponding to these proper maps.
So you claim, for instance, that any map of a pi scheme in the usual sense is proper.
Yes, exactly. Yes.
And did you claim things like the composition of, I forgot now, of shriekable is shriekable?
Yes, we claim that. I mean, Peter claimed it last time, I believe. Didn't give the argument, but it's quite straightforward. So let me continue the discussion. And so open immersion meant that, well, first of all, this J upper star functor, which you always have, this should be a localization. And the kernel should be just modules over some algebra.
So idempotent.
Yeah, it will necessarily be idempotent. It will also necessarily be a compact object because because by definition of a map of analytic rings, the right adjoint of this commutes with colimits, and then the.
So what's the definition of localization here? This is not in the. I forgot now. So
commutes other adjoints leave no small.
Yeah, just in the pure category theory sense.
So there is a notion of usual categories you can localize by multiplicative set, for example, and then sometimes it's badly behaved.
No, but these are like big categories, presentable categories, and the good definition is just what Peter said, that the right adjoint should be a fully faithful functor.
There is a right adjoint and it is fully faithful.
Well, yes. So, but this functor, well, I mean, we already know as part of the discussion of analytic rings that the right adjoint exists. So.
Yeah, because it is a nice functor with being presented as.
Yeah.
Okay.
Yeah.
We want to lift that joint.
Yeah. This implies that there's a left adjoint. Yeah. So let me. Yeah. So I'm going to continue the discussion. Right. And then, so we had this claim or this theorem. Oh yeah. So then the remark is that for a proper map, for a proper map pi, the right adjoint pi lower star is good. And what does that mean? It commutes with colimits, satisfies projection formula, i.e. it's d of y linear. So if you take an object in d of y and you pull it back, and then you tensor with something and push it forward, that's the same, well, yeah. So if you take an object in d of x prime, you can either, and an object in d of y, you can either pull it back, tensor, and then push forward, or you can push forward and then tensor, and those give you the same thing. There's a natural map, and you ask it to be an isomorphism. And commutes with base change. So in other words, a pullback of a proper map, first of all, is proper, and second of all, the formation of this lower star, this right adjoint, commutes with that base change that you can write down. And then for an open immersion, J, there exists a left adjoint. I don't know, J lower, whatever people use, which is good in the same sense.
What's the protection, J?
I don't know. I've seen this J lower sharp, J lower natural. Yes. It will be J lower shriek. Yeah. I mean, okay. I'll just yeah. Yeah.
No, there is the other thing, which is an adjoint, like sometimes for in duality theory, like an adjoint of F upper star. No, okay, it is not the bizarre, it is lower shriek, I mean, in usual.
Yeah, it is lower shriek.
Well, for the usual, it's an analogous to lower shriek in the. Yeah.
Okay. Right. And then the theorem that was discussed last time was so there exists a six functor formalism on F such that the collection of maps f x to y for which this extra functor you have, f lower shriek, from d of x to d of y is specified, is the class of shriekable maps. Such that for f proper, f lower shriek equals f lower star, and for J in open immersion, f. Now here's why I wanted to. Yeah, you know what? I'm gonna say left adjoints are J lower natural, and yeah, just so that I can make a non-tautological claim here. Yeah. Oh, thank you. Yeah, J, thank you. All right.
Six functor formalism contains the notion of proper, the class of proper, and.
It does not. So I'll explain in just a second exactly the manner and what the precise definition of this and how it's encoded and everything. In that encoding, it's not specified what is a proper map and what is an open immersion. It's just specified what is the class of shriekable maps. Oh yeah, and maybe a remark I perhaps should have made before is that there's the class of shriekable maps has good closure properties. So it's if we have x to y to z, say fg, then f and g shriekable implies g composed with f shriekable. G and g composed with f shriekable implies f shriekable. That's nice, so that a map between shriekable maps is shriekable. That's the way to think about this. Shriekable maps are closed under base change. Oh, and maybe I'll add one more. So if like f1 x1 to y, f2 x2 to y, fn xn to y are maps with the same target, then fi is shriekable for all I if and only if the map f from the disjoint union over I xi to y is shriekable. And these disjoint unions in this category, those finite disjoint unions in this category, they correspond to finite products in this category of analytic rings, and they're kind of just naively defined coordinate-wise. So so for finite coproducts. So maybe I'll do just, I think Peter discussed it last time, but just let me do a reminder of some example of this six-functor formalism. So let's take y to be sort of spec of the solid Z theory. Then let's take x to be spec of the solid ZT theory. With the natural map from x to y, which is just, yeah. Then we can take x prime to be spec of the solid ZT Z theory. So this is now this is so that we have x goes to x prime goes to y. Now this is proper, and this is an open immersion. And the complementary algebra A is equal to this Z Laurent series T inverse. And then, for example, J lower shriek of the structure sheaf of X is this two-term complex. And then that's also the formula for pi lower star. Pi lower star is just the forgetful functor, just forgetting that you have a module structure over ZT. And so intuitively speaking, this is functions on the affine line, and this is functions localized near infinity, so localized near the missing point. And so this is like functions on the affine line which vanish near infinity, so to speak, because you're taking a fiber. So that's kind of compactly supported cohomology of the structure sheaf on the affine line, so to speak. And this is what six-functor formalisms are supposed to be doing in general. They're supposed to be specifying some notion of compactly supported cohomology, relative compactly supported cohomology, which behaves well in families. So the key property of this F-lower Schriek is that it commutes with base change in complete generality. So the algebraic objects are proper even if you're dealing with something like the affine line, which is not proper in traditional algebraic geometry, but it's kind of compensated by the existence of this solid theory where you have a new version of the affine line, the solid affine line, which is not proper anymore. Yeah. Okay. So, and then there was the definition. So, a shriekable map satisfies Schriek descent if so you can take d of y, d of x, and then d of x cross y x, and then you continue like this. And then here you use the upper Schriek functors to define this diagram. So upper Schriek being the right adjoint to lower Schriek in every case. So this induces, so to the Schriek limit of the d of x to the n's over y. So the naive thing would be to consider the star descent. You'd want to know that an object in here is the same thing via pullback as a compatible collection. We actually asked for something different. It turns out to be stronger, which we'll show in the lecture today. That if you take an object here, you ask that it's the same as giving compatibly its Schriek pullbacks along this same diagram. So now that was the recap of last time. Now I can explain the goal for today. Goal. So, well, first goal would be to prove some Schriek descent results, i.e., identify some natural presheaves that have Schriek descent. So in other words, that some presheaf on aphanoids such that whenever you have a cover satisfying Schriek descent, which by definition means that d of y satisfies Schriek descent for upper Schriek, we want to define check what other kinds of descent properties that implies. Or, well, maybe I should actually give the definition, sorry. The Grothendieck topology of Schriek descent. So covers are given by finite collections fi xi to y. Sorry. of shrinkable maps such that F from the disjoint union of the xi to y has streak descent.
So this is rather a free topology on the underlying category.
Yes. So.
You take the generated topology.
Yeah. So I mean, so I could say a sieve is covering if it contains finitely many shrinkable maps satisfying this condition.
What about the composition of shrinkable? It's involved interchanging proper and open immersion.
Yes.
So is it?
It's quite straightforward, and the essential reason it's straightforward is there's a canonical candidate for the x prime, the factoring, because your x contains this algebra O of x, the structure sheaf, and then you can just take x prime to be have the same O of x, and then d of x prime should just be the full subcategory of d of O of x, consisting of things whose image in d of O of y land in d of y. So
you have like an open immersion and then a proper.
Yeah.
And then you say that this is like in adic spaces the canonical compactive. Okay.
Yeah.
So you take the ones. Okay. You use the other. Yes, okay. So you claim that, okay, thinking about it, you have a canonical candidate and you check it. It's
yes, exactly. Yeah. Okay. And the second goal for today is, well, then you want to be able to give examples of Schritt covers. So that you then can apply these descent results.
I don't remember if it was defined, this was a talk I saw in the web, but whether Scholze defined what six-functor formalism is exactly. I think he referred to Lucas Mann's work.
So I'm going to actually discuss it today because the precise way it's encoded will help give some arguments. So it's, in fact, the next topic that I'm going to turn to. Okay. So yeah, so this theorem, so the existence of this six-functor formalism on aphenoids follows rather immediately from work of Liu Zheng as reinterpreted by Mann. And so following Gates, Gorey, Rosenblum, Mann encodes six-functor formalisms in terms of span categories. So let me now set this up. So suppose given, well, let's say it could be an infinity category, C with all pullbacks. And a class of maps S in C stable under composition and pullback. Then, so I'm not going to give the precise description of the infinity category of spans. I'll give a kind of hand-wavy description. The precise description has been given by Clark Barwick. So as a complete Siegel space. I mean, well, or no, he did it as an, anyway, it doesn't matter. There's different ways of making it precise, and it has been done. So then we get a span category. Span C, let's say S all is the notation. So the idea is this is going to let you encode 6 functor formalisms where you have Schrieg maps defined for maps that lie in S, and you have star maps, like upper star, defined for any map whatsoever. So this has objects the same as in C, but maps X to Y given by diagrams. So X, Y, and then you put something in between, M, say, like this.
One of the maps is S.
Yes, thank you. Yeah, where this map, let's say this map is in S. Or would I rather say the other map lies in S? I don't know. You have to make a choice. And then the composition is given by pullback. So I'll just write it down like this. So you have a span from X to Y and a span from Y to Z. You want to make a span from X to Z, you just do the pullback here. And then, I don't know, a 2-functor formalism on C with respect to S is just a functor from span C S all to some category of categories. So i.e., to every object X, you assign a category, infinity category, D of X, say. We can call it D. And then to every span, you assign a functor. So, well, what is this doing? So there's 2 special classes of maps. There's the ones where you only have something interesting going on in the S part, and there's the ones where you only have something interesting going on in the Y part. And every map is a composition of, is canonically a composition of 2 such maps like this. So you can break this up into, well, it's kind of, yeah, X, M, 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 Y, and you can write this then as a composition of 2 of these. So if you kind of at least intuitively want to understand what your functor is doing on morphisms, it's enough to know what it's doing here and what it's doing here. And here, this is giving you a functor that you call, let's say this map is F. This is giving you a functor you call F lower Schrieg from D of X to D of Y. And here, it's, if this is F, this is giving you a functor you call F upper star from D of X to D of Y.
Stable under composition includes having the identity.
Yes, yes it does. That's what happens when you compose an empty set's worth of composable maps. And then and then it's a functor, so you get some relation when you have a pair of composable maps. And the functoriality amounts to the base change formula for the lower Schriek functors. So the fact that the lower Schriek commutes with upper star when you have a Cartesian square in your category. So 2 is a smaller number than 6, 2-functor formalism versus 6-functor formalism, but 2 is the essence of 6 in this case, because what are the other functors? So then that's 2 of the 6 functors, but then there's so if, well, base change formula and also compatibility of and upper star under composition. And it also encodes kind of compatibilities between the base change formulas and the compositions that you have on these things. So there's kind of higher order data implicit in here. Right, so that's 2 of the 6 functors you'd like to have, but then, so then that gives you these functors f lower Schriek and f upper star, but then for free, provided this admits a right adjoint, then you get the right adjoint as well, and provided this, provided this admits a right adjoint, then you get the right adjoint as well. And that gives you 4 functors. You don't need to encode them explicitly. They just kind of follows. And then the remaining functors are some tensor product operation you have defined on each of these, and then some adjoint to it, some internal arhom. And again, that if you have this and it satisfies a certain property, then it has some adjoint. So the only remaining question is how to encode this tensor product and the expected interaction of it with these functors here, namely projection formulas. Plus compatibility with lower Schriek and upper star. And for this, we use the symmetric monoidal structure on this span category, induced by product in C. So now I have to assume, I guess, maybe I assume C has a terminal object. I mean, I assumed it has pullbacks. I need products. Yeah, so let's say that C has a terminal object. See. Whoops. So yeah, that's Cartesian product in C, but it's not the Cartesian product in the span category anymore. It's just some symmetrical monoidal structure. And then request that your functor D from this span.
The precise way the symmetric model is structured depending on the span category breaks the symmetry between the two maps.
Could you say that again, Peter?
The precise way one makes product with your symmetric model structure on the span category breaks the symmetry of the two types of morphisms. Because at least if you take for S all maps, then so far the morphisms are symmetric.
Yeah.
But they will not be symmetric anymore for the symmetric monoidal structure, because only the pullback will be symmetric monoidal vector here.
Yes. Yeah, Peter was making a claim that the, well, I didn't finish the sentence, maybe, yeah. So we request that this be lax symmetric monoidal with respect to that tensor product we just defined here, and the symmetric monoidal structure here given just by Cartesian product of categories. So So the so what does this amount to? So the basic data is that you have dx cross dy should map to d of x cross y. So that's the direction of the laxness, if you were wondering. Plus, you know, some compatibilities which are conveniently encoded in this being a lax symmetric monoidal functor.
So in particular, dx plus dx maps to dx using the diagonal.
Yes.
And then you can probably reconstruct this by pulling back and
Yes.
entering over x
Yes.
plus y.
Yes.
But then one can wonder why you need the product in the category. It's not enough to specify dx plus dx to dx for every x in some coherent way.
Well, you need to encode the compatibility with the lower Schriek functors somehow. So that's extra data.
Okay.
Yeah. But yeah, indeed, if it were just, if S were like trivial class, then giving this would be the same as giving a symmetric monoidal structure on each of the values dx. So yeah, so part of this is, yeah, symmetric monoidal structure on d of x, and then the f upper star functors are also symmetric monoidal. As Ofer said, if you take x equals y, you can do this, and then you can pull back along the diagonal.
What about the object 1? Does it come for free? 1 in D of the terminal object.
Oh boy, yeah. I'm sure it comes for free from, so lax unital, I mean, there should be some unit. Yeah. Yeah. Okay. So yeah, I have to advance this story a bit. So yeah, so I said that if you just have these, well, really these 3 functors, ding, 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 satisfying certain properties, then you automatically get all 6 functors. And there's a very convenient way to organize the passage from 3 to 6. And that's it's a bit of higher categorical magic defined by Lurie. So this is Lurie's magic category. Called PRL. So I have to say a little bit about this and how it works. So here are the objects are the presentable infinity categories. Presentable means you have all small colimits, and you're in some sense controlled by a small subcategory. So in the sense that there's a small subcategory such that the whole thing is gotten by formally adjoining some sufficiently filtered colimits. So you should be kappa compactly generated for some kappa. And the morphisms are the colimit preserving functors. And then that's the equivalent to admitting a right adjoint. So let me tell you a bit more about this magic category. So PRL has all small limits. And the forgetful functor PRL to cat infinity preserves them. So that's nice. So limits in this category exist and are completely naive. So, but also, PRL has all small colimits. And this is the really remarkable thing, is that you can also access these colimits in a completely naive way. So there is, besides the naive forgetful functor, there's also a contravariant version of the forgetful functor, where you take C and send it to C, but then you take a functor from C to D, and you send it to its right adjoint. Yeah, and you can make this into an honest functor, so that's part of what Lurie does. And this functor preserves colimits, which colimits in the opposite category, so really it's limits, which translates to limits in cat infinity. So also the colimits in Lurie's magic category are just calculated naively limits of underlying categories, but with respect to passing to the right adjoints of the functors in your diagram. This is quite magical because in cat infinity or a category of categories or something, like colimits can be very difficult to calculate. Like for example, amalgamated products of groups are examples, of colimits in categories. And it's kind of a not so simple construction, but this is sort of easy. Right. So in particular, just to connect with what we had earlier, so this weird-looking condition of Schriek descent that we had for maps for Schriekable maps of aphanoids, it's actually the same thing as codescent. So codescent for the lower Schriek functors in PRL. And that's actually a much more convenient way of thinking about it. Maybe I should put this down here now.
And then this is the limit, but the limit is to be interpreted in the colimit in the sense of PRL.
Exactly.
Which is not this, which is, okay, which is,
okay. Now, there's more magic in PRL. There's also a symmetric monoidal structure. So, which is maybe the main theorem in Lurie's book or something. It's either, I don't remember which book it's in. I would claim that whichever book it's in, it's the main theorem in that book. my opinion. I mean, it's really, yeah. So it's a tensor product, and it's characterized by a universal property, just like you would expect out of a tensor product. So maps in PRL from C tensor D to E, that is the same thing as functors from the product, which commute with colimits in each variable separately. And then this tensor product on PRL also actually commutes with colimits in each variable separately. So you get a very nicely behaved tensor product on this category. So in fact, there's also a corresponding internal Hom is given by internal Hom from C to D is just the infinity category of colimit preserving functors from C to D. So. Note the mapping space in this category from C to D is what you get from this category here, sort of by only remember isomorphisms. So. But you can somehow recover the full mapping category by using this tensor structure. Well, that's one way of recovering it, at least. So in principle, PRL should be considered as an infinity 2 category because there's a whole category of maps between two objects. But you don't really need to remember the infinity 2 categorical structure because it's also just the internal Hom.
You mean equivalent isomorphism in this theory? I mean, they are up to almost okay. So there is infinity 2. Yeah, there was a reference to a paper on infinity 2 in some places, but I'm not. So do they define infinity n categories and all of this in general, or?
I haven't kept up with that. I don't know. Yeah.
Because I've seen some recent paper or someone I know about this infinity, or
yeah. I haven't kept up with the literature on infinity. So far, I've been fine with just infinity 1. So when the need arises, yeah. Okay. Okay, I want to continue a little bit more. So there's more. So if you have so now you can. PRL is now a tensor category. It's a category with a symmetric monoidal structure, and you can ask what is a commutative algebra in this tensor category. So meaning just it's an object in here equipped with some kind of symmetric multiplication. I mean, the basic data is this, but then there's some higher coherences and so on about it being sufficiently commutative. And what it means is that this is the same thing as C is a symmetric monoidal. Presentable infinity category and the tensor product on C commutes with colimits in each variable. Some people often call this, because this is a mouthful, people often call this a presentably symmetric monoidal infinity category. So, well, a basic example for us would be d of x for an aphanoid. And then you can consider, modules over C in PRL. These are sort of C-linear presentable infinity categories. So they're presentable infinity categories which are tensored over C. But that also lets you say that they're enriched over C in some sense. So, what do you have? You have like C tensor M goes to M. So that's the basic structure that you have here. But then if you have any two objects like M and N in here, you can make sort of a C internal Hom from M to N as some adjoint to a functor you can easily write down here. So maps from an object in C to this should be the same as maps from C tensor M to N in M. So it's a convenient way of saying you have a presentable infinity category where the mapping spaces are enriched to objects in C. Yeah.
Can you say again, if you have a C tensor M to M, how do you enrich the mapping space?
Oh, you want to, so you characterize this by a universal property, and then you prove there's a representing object. So the universal property is that if you have giving a map like this is the same thing as giving a map from C tensor M to N. I'm almost done with the foray into PRL. I promise it's going to be helpful.
So when you tensor like the derived category of modules over a ring, like dr1 tensor dr2, this should be, so as far as I know, if you tensor not over d of z, you get d of the derived tensor product.
Yes.
If you tensor like this, you get something big.
Yes. Okay. Yeah, so let me, that's, you get something bigger, well, unless you're in characteristic 0, so maybe let me give an example of, sorry, so that now, just to say, I want to continue the story just a little bit. So mod C PRL also has all limits and colimits. And mod C PRL to PRL preserves them, the forgetful functor. So completely naive, very simple theory. It also has a tensor product, which is a tensor product over C. So this is kind of a standard thing with some geometric realization of some standard relative tensor product. Let me give an example of a calculation. So if you have C as C alg PRL, and then you have R and S, which are commutative algebra objects in C, then you can make mod R C and or let's just say algebra objects. Yeah. And so you can consider left modules over R or S, and these will be in mod C PRL. So just R modules in C, S modules in C. And then mod R C tensor over C mod SC is just mod R tensor S C.
So in the definition of C linear thing, of course, you say C tensor M to M, but of course this comes with
there's more
coherencies, and there is a good way to formulate this system of coherencies in this. So we have to read some
higher algebra. You have to read higher algebra. But you know, it's not easy to read higher algebra, I know, but it's possible. People have done it. And someone even wrote it, which is even more amazing. Yeah. Okay. So, tensor products. Okay, so now I want to connect this to analytic rings. So note, so there's a functor. Or, well, maybe, so, yeah. So now I can say that the good way to encode, or a good way at least, to encode a 6-functor formalism is a lax symmetric monoidal functor from span C S all to PRL with this tensor product here. So we're no longer using the Cartesian product on cat infinity, but this tensor product on PRL. But it really just amounts to a condition on the kind of formalism we had in the other sense. It's just the condition that when you look at this d of x cross d of y going to d of x cross y, that should commute with colimits in both d and x and d and y, d of y separately. So it's just a condition on this formalism here, but it's best to think of it as being a formalism with values in PRL. Okay. Now I want to connect with our specific example. So note, so analytic rings maps to PRL by sending our triangle D of R to D of R. Well, in fact, as I already said, it maps to C alg PRL. But in fact, it maps to C alg PRL over a certain other commutative algebra object, namely derived category of condensed abelian groups. So everything by its nature lives over this derived category of condensed abelian groups. So we have a presentably symmetric monoidal category with a functor from this presentably symmetric monoidal category. And then I claim this functor commutes with colimits. And detects isomorphisms. Under, thank you, under, yes. Yeah, we're in the world of algebra, so I should say under, yeah, thank you. So we have this category here, and then we have an object in this category, and this notation means that you consider an object in this category together with a map from this object to to that object. So it's this some slice category or under or over category or something.
Every complex of condensed abelian group gives you, by pullback, some guy in D of R. Okay. All right, yes.
Yeah, I mean, it's just, yeah, I mean, the initial objects here.
You're saying what I wanted to say, right? On the sort, you have the initial object, and then when you have a functor product category with the initial object, it always maps to the over or under category over the image of the initial.
Okay, that's analytic ring to what's the initial object Z? Yeah, okay. So for Z you get D of condensed abelian. So you don't need then okay. Claim this factor.
So it's not the Fourier tensor.
Just a sec. So in particular, so if you want to, so the derived category of a push out, so or let's say A, B, R, so this is push out in analytic rings, which was this kind of slightly subtle operation in this perspective on analytic rings because you had to complete some pre-analytic ring structure and so on. But actually on the level of the categories, it's quite naive. So it is just this Lurie tensor product. This is the relative tensor product in PRL. So the proof is not so difficult. So let me indicate what's going on in the proof, just in this special case, which is really all we need. So in the case where A and B are both proper over R, I'm not assuming any shrinkability, but still let me use this language of proper maps. So in the case when A and B are proper over R, it's just an instance of this general fact here.
So did we say that commutative? And now got confused all this. So somehow you said the modules as limits and co-limits. And then did you say that symmetric?
Oh, I didn't say that C-alg has co-limits. I should have maybe discussed it, but it does. So, and as usual, push-outs are calculated by relative tensor products. Push-outs in C-alg PRL are calculated by relative tensor products in PRL.
Okay, and it has limits also?
It has limits also. Those are naive. Those are calculated in PRL.
It has co-limits, arbitrary co-limits also?
It has arbitrary co-limits, yeah, and filtered co-limits, or more generally sifted co-limits, are calculated again in PRL. So, yeah. Right, so in the case where A and B are proper over R, it's an instance of this general fact. In the general case, well, it's not shrinkable, but you can still factor, basically by definition, any map of analytic rings as a proper map followed by a localization. And then for localizations, it's quite easy to just check universal properties to compare the two sides of this. So granting the case of proper maps, then you just have two different quotients of your category that you're trying to identify, and you can just identify them by looking at the descriptions.
So for proper, you say that it is because in that case, in that case, for a proper map, this D of is the algebra. Our algebras over the bigger ones, and you said that algebras are. Yeah. No, but for any map of analytic rings, it's not a category. The D of the source is not algebras over some. Because in the case of localization, you have that the kernel are algebras over something, but not.
Yeah.
Okay.
And that was only for shrinkable maps also. Right. So let me make a corollary. So.
Analytic rings with shrinkable? No.
No, here, no shrinkable. It's not necessary.
I got. But you said something about D of A tensor B R equal D. This is for general, not necessarily shrinkable.
Right. But you can still use this reduction to the proper case. So you still factor as every map of analytic rings still factors as a proper map followed by a localization, but this localization won't have a left adjoint. I mean, it won't. But that doesn't matter so much for this argument.
Okay, so you don't need it. I thought, okay.
Yeah.
So for localization in general, you can somehow check it from granting all your stuff.
Yeah.
Okay, and then you. Okay.
Yeah. Okay. Oh yeah, I wanted to say this functor is not fully faithful for a technical reason. So to be fully faithful, you'd have to be able to recover our triangle just from the data of D of R with its tensoring over condensed abelian groups. So you can certainly recover the underlying condensed abelian group of our triangle because you have the unit object in here, and then you're tensored over this, so you can consider endomorphisms kind of, or the internal endomorphisms of this, and this will give you our triangle so over this linearity as an object in the derived category of condensed abelian groups. In fact, you can do more because this is the unit. You actually get this as in fact, you get it as a commutative algebra in this category, condensed ab. So you recover the underlying E infinity ring. But if you're working in this animated ring context, that's not enough to recover the animated ring. So there's not quite enough structure here in the animated ring context to recover the R triangle. But there's certainly enough to detect isomorphisms because, you get the underlying object. If you wanted to recover the animated ring, you'd have to do something like remember derived functors of symmetric powers, encode them somehow, say what kind of extra structure you have on this coming from non-abelian derived functors of symmetric powers, which is the kind of extra structure you get on modules over an animated ring compared to modules over an infinity ring, which only has the symmetric monoidal structure. Okay. Anyway, there's a corollary. So let's say you take I don't know, y in F, and then consider F shriek over y. This is the category of x mapping to y via a shriekable map. Then the sixth functor formalism. So we can again look at the span category of this, but now we don't need to restrict to shriekable maps anymore because every map in this category is shriekable by this kind of 2 of 3 property of shriekable maps. So I can just put all, which is a priori lax symmetric monoidal. It's actually symmetric monoidal. Wait, should I? No, I want to put a sorry, I want to. Sorry, I should do. Sorry, I want to. Yeah. Yeah. I have to remember the coefficient category, the linear structure over PRL. Yeah.
Why did you restrict the street overlaps now?
Because of what's going to come next.
Okay, but I mean, the fact that it is actually symmetric model would also be without this restriction.
Yeah, that's true. That's true. Yeah. But yeah, I wanted to. Yeah. Okay. Right. So, man, I had no idea it was going to take this long to get through this formal stuff. So a corollary is that for x to y shrinkable, then this object d of x in modules over d of y in PRL is dualizable with respect to the tensor product, the relative tensor product over d of y. And in fact, it's canonically self-dual. And with respect to this self-duality, the dual of so if you have x going to x prime over y, then the dual of let's say pullback so it should be a map. The dual of this map should be a map from the dual of x to the dual of dx to the dual of dx prime, but they're self-dual. So you just get a map in the other direction from d of x to d of x prime. This map is none other than the lower Schrieg functor. So the proof is you can check universally in any span category. Kind of span C all. So we have a symmetric monoidal functor. So if you want to, so the image of a dualizable object will be dualizable, and if you exhibit a duality pairing and co-pairing here, you get one there, and so on. So for example, so why is every object dualizable in this span, self-dual in this span category? Well, you have a unit, which is right. So. And then you have a co-unit, which is the same thing going in the reverse. And then you just check the triangle identities. It's completely straightforward. And then you can see that with respect to this self-duality of every object, that passing to the dual is just the same thing as transposing the span. So.
To define the self-duality, you need a pairing from dx and dx to either a map, what's the dx tensor dx to the unit, which is dy. So what's?
So yeah, so if you unwind this, then what you get is, so you have dx tensor dx. Implicitly, point is y here. So the c in this example will be this F Schrieg over y. So then you get, you have dx, tensor over dy dx. You pull back to dx, and then you do lower shriek to dy. So then we have a proposition, so that if f from x to y is a shriekable map, then the following are equivalent. So Peter said this last time, but he didn't give the proof, and now we're going to give the proof. So one is that f satisfies shriek descent. Two is that for all categories linear over d of y, so you have descent for m, so so if you take m equals d of y, you get star descent. Or in other words, what's that, Peter?
That's a map is an equivalence.
Oh, thank you. Yeah, yeah. So by definition, shriek descent means that you have descent with respect to this weird pullback, these weird shriek pullback functors on these d's. But then the conclusion here is that you get it also automatically for the star pullback instead. And then the third condition is kind of a categorified version of star descent. So it's called two descent, studied by Gates-Gorey and Rosenblum, which is kind of a remarkable thing. So that if you take this whole category, then that's the same thing. Then that assigning to y this category also satisfies descent. So. In the sense of infinity 1, but if you have, I'll explain more or less why it's the same, requiring this for infinity 1 and for infinity 2. But I'm not going to try to say I know what an infinity 2 means. So, well, in the proof that 3 implies 2, I mean, well, yeah.
So, do you have also a shriek version of 2?
Yes, you have a shriek version of 2. Yeah, but that's completely formal from 1. So let's get into the proof, and then it'll become more clear. Or maybe let me state a corollary first. Or maybe, yeah. So a corollary is that a pullback F satisfies Schritt descent implies any pullback also does. You can see that from 2 and using this symmetric monoidality that we discussed. But also, I think in the course of the proof, a simpler explanation will arise for why Schritt descent is closed under pullbacks. So that's important for using this to define a Grothendieck topology in the first place. Okay. What?
Why the pullback? Because the D of the
Yeah, because the pullback in analytic rings is already calculated by a relative tensor product. So if you took, for example, M to be D of Y prime, then this would give you star descent for the pullback. But you could take M more generally to be any D of Y prime module, and yeah, and then you'd get, so you'd see that condition 2 is stable under pullback, under base change. So what do we have? We have Schritt descent, but I explained that the best way to think of that is that you have this colimit in PRL. In PRL. But I also explained that colimits in module categories are the same as on the underlying, so that's the same thing as modules over D of Y in PRL. Now take internal Hom out. To M for any M in mod D of Y PRL. Then this, well, on the right-hand side, we're taking internal Hom from the unit to M, so we just get M. And it's being identified isomorphically with some limit, so the colimit pulls out of the internal Hom, some limit of internal Hom from D of, whoops. But, sorry, what did I just write? D. But then I explained over here that this thing is self-dual. It's dualizable and in fact self-dual. So then you can actually move it over to here with a tensor product. So this is internal Hom in D of Y, M. And I said that the manner in which it's self-dual is such that it converts Schritt functors into lower Schritt functors into upper star functors. So then this is exactly 2. I guess, in fact, this is a proof that 1 is equivalent to 2.
And of course, you have to verify that the cone that you get is really the expected one in some higher set.
Yeah. Yeah, you do it universally in the span category, kind of this identification. Yeah.
The self-duality turns this system to the other, to the expected one.
Yeah.
But there is some delicate point.
Absolutely.
Okay, it's not because of the higher nature of the thing. I'm not so sure what you have to check. So.
Yeah. Yeah, you have to produce the data coherently. You have to produce the data making this coherent identification of the dual of this, of this self-duality and the dual of this identifying with this. You produce it universally in the span category, and then you map it into modules over D of Y. I haven't actually done that, but there's also another argument for this, so that doesn't require this stuff. I just wanted, I mean, it can be done, I'm 100% sure, but yeah, I haven't actually done it. But there's also another independent argument for this, which doesn't require such things. I just thought I would present this because it feels the clearest to me, even if it's slightly difficult to make technically work. Okay. Right. Okay. And then, so 2 implies 3. So, yeah, we have to check this statement here. So there is a, this. The map has a right adjoint, which is basically you take a system of modules here, and you forget them all to d of y, and then you take the limit in this category here. So it's like taking a system of modules mn, and then you go to the limit of the mn. And you want to check that the unit and the co-unit of this adjunction are isomorphisms. So the unit being an isomorphism, this is exactly 2. For the co-unit being an isomorphism, so it's true after if you base change up to x, then the co-unit is an isomorphism. Because, so d of x is dualizable over d of y implies that you can pull the limit out. And then 2, the cover is split on pullback to d of y, or d of x. And then 3, there's an obvious base change property. So, yeah.
Base change property of, you mean?
Yeah, I mean that the right adjoint, say from mod, so you have a mod d of y PRL, you have a pullback functor to mod d of x PRL, and then you have the right adjoint, which is the forgetful functor, and that forgetful functor commutes with base change, or where base change means push out in C-alg PRL. So it's just like purely algebraic base change.
No, I don't.
Yeah.
So first of all, you say the co-unit means the map from something to the inverse limit of the pullbacks, yes?
Yeah. Yeah.
The co-unit.
Right. So you have, yeah. So you have a collection of things here. You take its limit and you base change it back. I guess I wasn't. Yeah. I think you're right. I didn't set this up quite correctly. So then you have a map of systems here, and you want to check it's an isomorphism for all n. And then maybe I was, yeah.
There is a confusion of unit and.
I think your unit and co-units are exchanged.
Are they really? Oh, wait, no? Are they?
No. Unit is an isomorphism.
Sorry.
No. The unit is the right one. So the map from a guy to Okay, the unit is the right one. The co-unit
Yeah.
means you have a system and you want to
Yeah.
compare it to the pullback
Yeah.
of its limit,
Yeah.
which is okay. And then you say,
So I was giving the argument when n equals 1, and I should have, yeah, sorry, I think,
okay, so let's go again. The co-unit
Yeah.
being an isomorphism is,
yeah,
okay, so we don't say after going to dfx, because
Right.
this is confusion with the co-unit,
Yes.
and we are
Yes.
completely, okay, then let's see. Because it's dualizable, any limit commutes with no, but this is
I
something.
actually find this one to code initially. You should base change from d of y to d of x.
Oh, I should base change the whole system from d of y to d of x. Yeah, yeah, that's good. Yeah. No. Yeah. So thanks. Yeah, yeah. True. After base change to d of x. Yeah. In other words, you take this whole collection here, and you base change to d of x. Right. Yeah. So.
The base change, you mean tensoring with d of x in your sense.
Yes, tensor over d of y with d of x.
And then the limit can be commutes, so you can do it in the system after tensoring. And after tensoring, you get the system of derived categories for the fiber product space, affine, so to speak, spaces, because we said the D is somehow D of the fiber product is D of the tensor product of the D's for affine things, yes?
Yeah.
Or not? Oh, yeah, okay.
Yeah.
And then the covering is split. And so as in usual descent theory, this means that you can play with some homotopy to, okay, then and so what is point 3? The base change property.
Oh, that's so that you can identify when you tensor the thing up to d of x, that you can identify that system with the corresponding system for the pullback of the cover to d of x. So it's nothing. I mean, it's purely formal.
Okay, so here there is no. Okay, but kind of it's hard to be 100% sure about those things.
Well, actually, yeah. I mean, I think actually this argument, I believe, is in Keel Matthews' paper. Yeah. And maybe it's also in Gatescoy, Rosenblum, and so on. I mean,
Which Matthew?
Galois.
That Peter referred to some in the last.
It's the original reference for descendability. It's like, yeah.
Yeah, the reference I wrote down last time, that one of stable homotopy theory.
Yeah.
There was something in Bach-Scholz where they proved
Yeah, then they characterized the descendable maps in some finite type context. Yeah. Okay, okay. It's okay. We'll continue again after Christmas. Right, okay, so then then this collection and then the image of this and then this, those two things are the same isomorphic after you tensor to dx. But then 2 also implies that tensoring dx detects isomorphisms. So done.
2 also implies that detects isomorphisms are 2 also. All right, okay. Yes, okay.
Yeah, it's a bit of magic, but yeah.
And you get also now a strong form of 3 with the infinity 2.
Right, so let me quickly explain the argument for 3 implies 2, which is kind of more or less explaining why you get a strong form of 3. So if you take mapping spaces, so yeah, if you have, let's say you have what's that, Peter?
It's an already because we said that the unit being equals is exactly 2. Right? And if you have the first of categories and the unit.
Oh, that's true. Yeah. So I don't need to. Yeah, you're right. Yeah, unit being. Yeah, you're right. Oh, yeah, Peter. I was going to give a different argument. Peter's right that this argument shows that 2 is exactly the claim that the unit is an isomorphism. So, so clearly 3 implies 2. But I was going to give a different argument, which maybe also explains why you get an infinity 2 categorical.
3 implies 2 because.
So 3 means that this functor is an equivalence, but this functor has a right adjoint.
Yes.
So it being an equivalence is the same as the unit and the co-unit being isomorphisms. But when you unwind what it means for the unit to be an isomorphism, you get exactly 2. So clearly 3 is stronger than 2.
3 as a right. The right adjoint being okay. Being what? The inverse. Okay. So and then being the unit. Okay, so this actually shows that you have 2.
Yeah.
Without giving another proof.
Yeah.
Okay, you said that you have another.
Yeah, there's another way of seeing it, which is, I mean, one way of, okay, so if you have just 3 in the infinity 1 categorical sense, what do you get? You get that if you have m and n in mod d of y PRL, then you get the mapping space in mod y d of y PRL from m to n is the inverse limit of the corresponding mapping spaces after you do the base changes. And this is the set of objects in some internal Hom. So it's a priori weaker than the claim that for the internal Homs you get a corresponding limit statement, which would be kind of the infinity 2 version of this. But if you can just tensor this with like presheaves on delta n for any n, and then you'll get the fun from delta n to this. And then if you let n vary, then you recover the whole complete Siegel space associated to this category just in terms of mapping spaces. And yeah, so I'm saying what you get a priori is the space of objects in this infinity category that you're interested in. But if you then vary the source by tensoring with presheaves on delta n, and that tensoring kind of commutes with everything, then you get not just the set of objects, but the set of morphisms, the set of composable pairs of morphisms, the set of et cetera, et cetera, et cetera.
And elaborate, saying again that the symmetric model structure of these things determines the 2 morphisms.
Yes. Yes. Yeah. Yeah, I was just giving it a little more explicitly. Yeah.
And so d delta n is presheaves on what is it? Presheaves in which sense?
I mean, delta n is like a finite category, and I have to put it in this big world of PRL, so I just take presheaves of whatever spaces. I mean, if I want this to be a tensor over d of y, then I should do presheaves with values in d of y.
And delta n is the simplicial finite category or its opposite? Which one?
Yeah, good question actually, because maybe I want to, but they're isomorphic, so maybe I will. Yeah. Okay, so this was roughly half of what I wanted to do today, so let's go for another 2 hours, shall we? No, I'm kidding. Yeah. So yeah, we're taking a little break. I think the next lecture we scheduled for the 10th of January, which is a Wednesday. So I'll be, I guess, picking up and actually finishing what I intended to do today. So this was some consequence of Schritt descent. Maybe I just mention one more corollary of this, which is that topology of Schritt descent is subcanonical. So that affinoids will embed fully faithfully into the sheaf category. So yeah, so those are some consequences of Schritt descent. You get some very strong star descent results. And next time I'll talk about examples, how you produce examples of Schritt covers.
So logically, so just to get this, so you said that in 3 you have a statement in the world of infinity 1, then you tensor it with d of delta n, you get it in the sense of infinity, so at least the mapping spaces, the mapping not the mapping spaces, the mapping categories
are the limits of the corresponding ones.
Whose group are the mapping spaces, but the mapping categories are equivalent.
Yes.
In 3,
yes.
And from this you deduce 2. How do you deduce from 3 to 2?
Oh, because you could just take the mapping infinity category from the unit object d of y to m, and then.
Okay. The ones you know the mapping spaces, you get 2 in another way, so to speak.
Yeah.
And Peter said that if you have equivalence in infinity 1, then infinity 2 follows by. He said something different than your argument, or?
I don't know, but yeah, one thing to note is that there's 2 parts. If you want this to be an equivalence of infinity 2 categories, you need it to be fully faithful and essentially surjective. But now fully faithful means isomorphism on mapping categories. That we just explained. But essential surjectivity actually follows from just the infinity 1 statement. Because here you just have a bunch of, so then,
Fully faithful in the infinity 1 sense is weaker than fully faithful.
Exactly. A priori, but in contexts like this, it's actually equivalent. So.
You mean when you have tensor?
When you have some kind of a, when you can perform this trick. Well, okay. Thank you, everybody. See you after the break.